Wow, that's blurry. Let's see. Okay, this is 1216, worksheet 1216. This is a worksheet that changes every year. This is last year's free response questions from the Calc AB test. All 6 of them. This is really good practice. You should try these before watching this video. See what you can do. If you get stuck, move on. See if you can do it within the time limit. 90 minutes, about 15 minutes average. Some will be quicker, some will be slower. The first two are graphing calculator, and the graphing calculator has to be put away after 30 minutes, but then you can still work on them. Anyways, see what you can do. Try your best. See what you're ready for and what you get stuck on, and watch this video, and you might be like, oh my gosh, that was obvious, or oh wow, that was weird and hard. So I'm going to do these videos now. And so the first two are graphing calculator. You're allowed to use them. That doesn't mean every part will require one. And if you run out of time in your graphing calculator, most points are for setups anyways. So fish enter a lake at a rate modeled by the function E. Fish leave the lake at a rate modeled by the function L. Both E and L are measured in fish per hour, and T is measured in hours since midnight when T equals 0. So this is totally a rate model, right? I mean, they're even using E and L for entering and leaving, just like we usually generically do. So let's see. Let's see if we can just write the rate model right now. So the rate model would be the amount of fish equals the amount of fish at time 0, which I believe is... They didn't say. So I guess we'll wait. Equals the entering rate, which is actually called E on this one, from 0 to T, minus what? Minus all the leaving changes. So this is our rate model. We don't know the initial amount. We're not going to assume that it's 0 right now. We might be told later what it is. Okay, so that's just our rate model, just to kind of get us thinking about what it looks like. Now, A says how many fish enter the lake over the 5-hour period from midnight to 5 a.m. Give your answer to the nearest whole number. Let's not lose a point just because we do so good at 3 decimal accuracy, but ignore special directions. So usually it's 3 decimal accuracy, no matter what you feel about it, unless they tell you otherwise. So this is just the entering amount. So we're just doing 0 to 5 of the entering rate. Now, you need to write this down with the limits and the DT and all that stuff. You don't have to write the whole equation out. Now, the point breakdown here is going to be 2, 2, 3, and 2 to give you your 9 points. So writing this down right here is 1 point. If you don't write it down, you don't get that point. I'm going to put both of these equations in my calculator because I'm probably going to have to do multiple calculations with them. I might not graph them, but it'll be helpful to have these in here. I can do the whole vars, y-vars thing and speed things up. And so I'm going to be very careful and double, triple check that I entered these in correctly. Okay. And then I'm going to go back to the home screen and we're going to do... You got to remember which one's in which. Math 9, vars, y-vars, function, y1, comma x, comma 0, comma 5. And there's your answer. Now I'm going to go ahead and write it in a little more accuracy of 153.4576901. I might need this for another calculation, but I'm going to write the answer. I'm going to say, okay, well, 153 fish enter the lake from time t equals 0 to t equals 5 hours, or midnight to 5 a.m. Either way. And so that's your other point right here. Now, something I haven't really mentioned before, but I'm going to start mentioning more, is that we probably shouldn't box our answers on free response. I mean, I guess it's okay, and I always do it just because we usually box our answers in general. But I've heard that potentially could cause you to lose some points on the AP test. Like if you box the wrong thing, like if you have the right answer somewhere, but then you did something else and you box that as your answer, that can like somehow work against you. So it probably won't hurt you, but there's the small chance that it might not help. So anyways, you don't need to box your answers in for your response. So might as well just not box them on the actual AP test. If you do, it's probably fine. What is the average number of fish that leave the lake? Average number of fish that leave the lake over the 5-hour period. So, we could think mean value theorem, but you could also just kind of think, just common sense. Like, okay, how many fish left the lake, and divide by the number of hours, and that would be the average number of fish that leave the lake per hour. So, but anyways, if we integrate the amount of fish, because they want fish leaving the lake per hour, they kind of want the average rate. So they want average LT. If you read that correctly, they want average LT. And so we're going to integrate. Mean value theorem just says, okay, well, integrate the thing you want to average, LT, from 0 to 5, smooth it out. Smooth out height is what you want. Divide by the base of the rectangle, and you get the height of the rectangle. So you need to write this down, because this right here is worth a point. Your setups are worth as much or more than the actual answers. And so this is going to be very similar to the last problem, but we're going to do, so I'm just going to do copy paste, but then I'm going to go over here, second insert 1 divided by 5. Oh, shoot. Oh, I messed it up already. Whatever. Okay, we'll try it again. Now I'm getting older stuff. I'll just redo it. 1 divided by 5, math 9, bars, y bars function, y2, comma x, comma 0, comma 5. Don't forget the 1/5. So that's 6.059037771. I'm just writing all that down just in case. Now, did they tell us to round to the nearest whole number on this problem? No, so you should not. Hopefully, if you do, you're going to lose points. So I'm going to write the answer kind of nice. The average number of fish that leave the lake from midnight to 5 a.m. or you could use t equals 0 to 5 hours, is 6.059, round truncated 3 decimal accuracy. What are the units? Fish per hour. This is average L. L is fish per hour leaving the lake. So 1 more point for your answer. Part C says, at what time from 0 to 8 is the greatest number of fish in the lake? Justify your answer. So as far as the rate model problem goes, this one's, part B was part A was so predictable. Part C is very predictable. And so we're trying to find the greatest number of fish. We're trying to find max fish in the lake from... Now, did they say anything? Fish in the lake. So they don't really say how many fish are in the lake at time 0. And we still don't know, but I think we'll be able to find this answer. So we're trying to find max fish for 0 to 8. So these are your endpoints. So we're going to do EVT. I'm going to write everything out very carefully, show the setups, show the calculus logic behind things. So these are the endpoints. We need critical points. So I'm going to go ahead and just write our rate model down. Now, I don't know. I don't remember seeing anywhere that said there was no fish in the lake at time 0. But plus 0 to t et dt minus 0 to t lt dt. And then I'm going to say, well, we want the derivative of that, which is going to give you et minus lt, and that is fundamental theorem of calculus part 2 equals 0 undefined. You actually want to write all this stuff out. You want to write that the derivative is this equal to 0. Now, I don't think it's going to equal undefined. So then from here, I mean, you could say that et equals lt, but don't jump to that. Show this first, okay? And in fact, that's a point right there. Having shown that is a point. Sets et minus lt to equal to 0 is a point. So you have to have et minus lt equals 0 in your work. Now, I'm going to find this critical point now with my graphing calculator. It's going to be an intersection of those two curves. And so I guess I'll go to window, 0 to 8, and then we could do zoom fit. I don't know how tall, big these graphs are. And this does take a little extra time to do zoom fit because it pre-calculates otherwise. Now, this is really dense, so I think I'm probably going to change my axis. So that's the entering rate, that's the leaving rate, this is their intersection. I mean, so from here, you could just say, okay, let's find the intersection. We could go to window and make it a little nicer. We could probably say -1 to, I don't know, 50 would probably be fine. And then that way you see the x-axis. Not that you would have to do this, but it does give a little nicer version of that. So we're going to use our calculator to find this intersection right here. So second calculate, number 5, intersect, first curve, second curve, give it a guess. It's 0 to 8. It looks like it's around 6.5 or something. That's quicker than moving the cursor all the way over. So it is 6.203564. Carry extra decimals, more than 3, because you're going to use this in your work. And they do in the scoring guidelines too. So now we're going to make a table. So this is our critical point, by the way. Critical point. So we're going to put our endpoints and our critical point, 6.203564 and 8. And we're going to plug them into our rate model. Now, usually we have an initial condition that we don't have this time, but we can still figure out where the max happens. I don't know if we'll know what exactly it is, if the initial condition is supposed to be something other than 0. But if you plug 0 in here, you're going to get A0, initial condition, whatever that is. If we plug, so we're going to go to the home screen here, and I'm going to go math 9, vars, y vars function, y1, comma x, comma 0, comma 6.2035644, minus math 9, vars, y vars function, y2, comma x, comma 0, comma 6.2035644. And this should give us, now, there's initial condition still there. So I'm just going to add it to that, 135.0149199. Okay, we're going to do it again and plug 8 in for the second limit. Delete, 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 delete. 8 here. Delete, 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 delete. Okay. Enter. So this one's going to be A0 plus 80.919973. Okay, so we're looking for the max. This is the max, even if we don't know exactly what it is. But maybe I'll try and, we weren't trying to find the max, we're trying to find the time. But I'm always going to write my answers very thorough. So I'm going to say the greatest number of fish in the lake for times 0 to 8, because that's important, right? Hours, I'm going to put units in here, is the amount at midnight plus 135.014 or 5 fish at time t equals 6.203 or 4 hours. Round or truncate comes out different this time. And then I got to, by extreme value theorem, write it out. Don't give abbreviations. By extreme value theorem, you need to say this. And how does extreme value theorem work? By checking endpoints and critical points. So, there you go. That's part D. So that was 3 points, 1 point right here, 1 point for the answer, and 1 point for the justification. So this right here is a point, and then this work and this justification is a point. But I don't know, kind of a typical rate model kind of question, max or min. D says, is the rate of change in the fish in the lake increasing or decreasing at 5 a.m.? Explain your reasoning. Now it says, is the rate of change increasing or decreasing? So if they ask you if something's increasing or decreasing, that means the derivative of it is positive or negative. But it says, is the rate of change. So we're looking for the rate of change of the number of fish. So the rate of change of the number of fish is A prime. And that's the rate coming in minus the rate going out. But they're not asking, is the overall number of fish in a lake increasing or decreasing? They're saying, is the rate of change increasing or decreasing? So we actually have to take the derivative of the rate. So this is what we're talking about right here. This is the derivative of the rate of change. And the value it has at time 5 will tell you if it's increasing or decreasing. So this is a little, I could see some people just doing the rate at 5, which is a common question. So you gotta read it carefully. Is the rate of change increasing or decreasing? Now, I could do this on my calculator. I could do both of those at the same time. We could do math 8 and derive vars y vars function y1, comma x, comma 5, minus math 8 vars y vars function y2, comma x, comma 5. So this is doing the derivative. It comes out to negative 10.72278. And it's negative. So that means the rate of change is decreasing. So we need to say that and justify it. Our work right here is going to help us justify it. You really should have some numbers to back up your answer. So I'm going to say the rate of change in the number of fish in the lake is decreasing. So that's the key word right there, decreasing at 5 a.m. It's good to mention when it is. Is it decreasing all the time? No. Since E prime 5 minus L prime 5 equals negative 10.722 fish per hour is negative. The derivative is negative. That's why it's decreasing. So that's 2 points. 1 point for the answer, that it's decreasing, and 1 point for the justification. They specifically said considers E prime 5 and L prime 5. So you needed to have this in your work to get that point. And then the other point was the answer and justification. So that's the first problem from last year. Let's take a look at the next one. So we used our calculator a lot, by the way, and used it to do some things really quickly. I mean, could you have integrated and taken the derivative of those functions? I think you could have integrated E. I think you could have taken the derivative of both. I don't think you could have integrated L. So, but even if you could, don't. Okay, number 2. This is a graphing calculator problem 2. Right away, you see a table. And you should be thinking, okay, we're going to be doing estimation techniques. Riemann sums, trapezoids, estimating the derivative by taking the slope of a secant line between 2 points near the point we want. Also, right away, I think we can tell this is a velocity. This is a motion problem, one-dimensional motion, rectilinear motion. The velocity of particle P moving along the x-axis, so this is left-right motion, given by the differentiable function Vp. That might come in handy, that the fact that it's differentiable. We might need to state that as justification for using some theorem or test. Is measured in meters per hour, and T is measured in hours. We should be putting units on all our answers. I wouldn't wait for them to ask you. Selected values of V sub P are shown in the table above. Particle P is at the origin at time 0. So that means the position of particle P at time 0 is 0. Okay, so initial condition. A, justify why there must be at least one time t between 0.3 and 2.8. So we're looking specifically at that portion of the table where the derivative of v, the acceleration of p, equals 0 meters per hour per hour. Now, there's probably only 2 things that would be useful in this, either mean value theorem or intermediate value theorem. Now, intermediate value theorem is the easier one to use, and that would be if we actually had acceleration values here and we could prove, okay, well, here it's positive, here it's negative, so it had to go through 0 at some point. That's intermediate value theorem. Mean value theorem is we're going to try and find the average v prime, and then by the mean value theorem, we know that it should happen at least once. The actual value should equal the average value at least once. So I think we're going to go with mean value theorem. So we're going to try and find the acceleration of p average. I think it's good to write this stuff out. Average, which equals v prime p t average. So this is the average of a derivative. So you could do the regular mean value theorem, but there's a nice, more convenient, quicker way to jump to what you're going to eventually get. If it's a derivative and you have those values, then we could say, okay, well, let's do v sub p at 2.8 minus v sub p at 0.3, and then divided by 2.8 minus 0.3. So we're just finding the average of the slope of a line connecting the endpoints of the v graph to get the average slope of v. The values in the graph are 55 and 55 over 2.8 minus 0.3, which gives you 0 over 2.5, which gives you 0. And you're going to get 1 point just for having done that. Okay, key. The point breakdown here is 2, 1, 3, 3. So we got 1 point there. Now we need to kind of now to use mean value theorem, there's some conditions that have to be true. And so to potentially get the best justification credit, you need to not only say that you're using mean value theorem, but you got to say why you're even allowed to use it. Because sometimes we're not allowed to use it. Sometimes they give you problems where you're not allowed to use it and things go weird. Now, the reason we're going to use this is V has to be continuous and differentiable to use this. If there's a corner cusp, this isn't necessarily going to happen. So since V sub PT is continuous and differentiable requires continuity. And the only reason we could say this is because they told us up here that it was differentiable. That's the reason they told you. If they didn't tell you that, you couldn't be doing what we're doing right now. It's continuous and differentiable on the time interval that we're interested in. It might be good to specify where the things are true that you're saying are true. Since that's true, by the mean value theorem, there must be at least one value C on 0.3 to 2.8, and we leave off the endpoints. It's an open interval when we're dealing with derivatives, such that the derivative at C equals the average derivative, which we've shown equals 0. So that's a good explanation. So 1 point for having shown this, and then 1 point for your answer and justification. Okay. B, use trapezoidal sum with 3 subintervals, 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8. So that's not using the whole graph, the whole table, to approximate the value of this. Now, by the way, a lot of times they would ask you, well, what does that represent? And you'd say, oh, that's the displacement, the total displacement of the particle P in meters from time t equals 0 to t equals 2.8 meters. And they're not asking that this time, so I think that's actually kind of strange. But I'm going to draw, so we're trying to estimate this. And I'm going to draw a little picture somewhere. The picture is not going to give me credit. It's just going to help me now. This is going to probably mess some people up. They're going to be like, what do we do? So 3 subintervals. And now the first value at 0 is 0. And then 0.3, it's at 55. And then at 1.7, it's at negative 29. And then at 2.8, it's back up to 55. So it's kind of weird. Now, trapezoids, you connect the endpoints of the slices to create trapezoids. And on this one, it doesn't even look like we get any trapezoids. We get a couple triangles. Now, triangles can be seen as trapezoids where one of the bases is 0. And you can get one side that's positive, one that's negative, and it'll work out. If you just treat it like a regular trapezoid and use one base that's negative 29 and one that's 55, it will give you the correct area. You don't need to use slope to figure out where this happens. It definitely is not halfway between the endpoints. Don't treat these like triangles. Just treat it as one big trapezoid. So the work is going to be the average of the bases, 0 plus 55 over 2 times the height is sideways. And then the average of the bases, the next one's going to be 55 plus negative 29 over 2. And that base is going to be 1.4. And then the next one is going to be negative 29. Oops, I messed that one up. Negative 29 to 55. Those are the two bases. Average them, add them, divide by 2, and then times that height is going to be 1.1. So you need to show this work. You need to show the work. The picture isn't required for any credit, but that's probably going to help you get it right. But this right here, showing the trapezoids being calculated, is 1 point. You want to make it very clear. Don't just have work floating around randomly on your page. All your work on free response should be labeled and organized and very clear what it is. Now, I do have a calculator to help me. So I'm going to go ahead and use my calculator to help me do this. I mean, I could probably pull this off without a calculator, but I might make more mistakes and I would potentially, it would just take longer. So 55 divided by 2 times 0.3 is 8.25. And then 55 minus 29 divided by 2 times 1.4 is 18.2. And then negative 29 plus 55 divided by 2 times 1.1 is 14.5. 14.3, and then I'm going to go ahead and add all those up on my calculator. So 14.3 plus 18.2 plus 8.25 is going to be 40.75. The units of this, if you're integrating velocity, it's meters per hour times dt is hours. This is meters. And this is displacement, by the way. Not that they're asking you for that. So that was 1 point total. So they're not very generous with that, but show your work, get your answer. So they said, answer using trapezoidal sums. So you got to have the right answer, and you got to show trapezoidal sums. Now, they even show their work a little more detailed. They actually show VP this, VP that, and then they plug the numbers in, and then they give the answer. I don't think you have to do that, but I would at least be showing the trapezoids being set up. C says a second particle Q also moves along the x-axis. So that's velocity from 0 to time 4, which is the same times that we have in the table, is given by equation. So now they're giving you an equation of the velocity of a different particle. They're just giving you the formula for it. And it says find the time interval during which the velocity of particle Q is at least 60 meters per hour. And then it says find the distance traveled by particle Q during the interval when the velocity of particle Q is at least 60 meters per hour. So we're trying to figure out when is VQ, which equals 45 square root of t cosine of 0.063 t squared. When is it at least 60? That's greater than or equal to 60. Now, you could try and solve that by hand. I don't think you want to. I don't know how well that's going to go for you either. But we can use our calculator, put this into the graphing screen. Cosine 0.063 x squared, close. And then I'm going to graph another line that's 60. I'm going to graph these two lines. And then when this graph is above this line, that's what we want. Now, the window is going to be 0 to 4, they said, right? And I don't know what the y value is going to be, so I'm going to do zoom fit. And then I might change it just to make it a little nicer after this. But this is a quick way to get a graph of it. So there's your velocity. This looks like a pretty good graph. You can see the x-axis. There's the 60 line. So this is the chunk of the graph that we want. Now I'm going to just draw a picture of that just to help me keep track of stuff. It's not to really get me any credit. These sketches I draw. So that's 60. And then this graph goes like that from 0 to 4. And this is the velocity of Q, by the way. Right? We're ignoring particle P right now. So we want to find this point and this point, and it's at least, so that means including. So, and that's the portion of the graph we want. So it's easy to do now that we have this graph. We can go second, calculate intersection. First curve, second curve. Let's see, I'm going to write this all down. 1.8661815, comma 60. And I'm going to do this one. I'm writing down extra decimals because I'm going to have to use these for another calculation in a minute. First curve, second curve. This one's closer to like 3.5, I think. 3.5191744, comma 60. So the first answer is, it says find the time interval when the velocity of particle Q is at least 60 meters per hour. So we're going to say velocity of particle Q is at least 60 meters per hour on the time interval 1.866, comma 3.519, round truncate comes at the same time, hours. Okay, so that's one answer. And point-wise, that's your first point out of 3 points on this part. And then it says, find the total distance. Find the distance traveled. Well, that's easy. Distance is the integral of speed, the absolute value of velocity, and in this case, v sub q, from on the same time interval, they said. So we're going to go 1.8661815 to 3.5191744. So I'm carrying the extra decimal places because we're trying to do a calculation now. This is important. That's a point. Okay. The setup, you need the absolute values. If you don't, that's not distance, that's displacement. You need to put V sub Q, or you could write the whole thing in there, but the quicker way is to name it V sub Q, but put V sub Q, because otherwise it's not clear if it's V sub Q or V sub P. Now on my home screen, I'm going to go Math 9, and then I'm going to go absolute. You guys know where to find it on your calculator. My calculator is under the Math menu, num, ABS, bars function y1, close the absolute values, comma x, comma 1.8661815, comma 3.1591744. So just typed it all in, and there's my answer. 106.108 meters. Or you could have done 106.109 if you want to round. And the answer is your other point. So you got a point for that one, point for your setup, point for that. D says at time t equals 0, particle Q is at position x equals -90. So x sub q 0 equals -90. Now we also know, by the way, up at the beginning, and I don't think we've used this, x sub p at time 0 is 0. Maybe we're going to need that. It says using the result from part B, that was the integral, the estimate of the integral, and the function VQ from part C, approximate the distance between the particles P and Q at time 2.8. So the distance between the particles at time 2.8 is going to be the absolute value of xq 2.8 minus xp 2.8, or the other way around, but then you just do the absolute value to make sure it's distance. So it comes out positive. That's what we're trying to find. Now, we can't find the exact value for these, or we can't do it for P because we had to estimate it, but we're going to do that. So to find this value, we got to find these two separate values first. So x, the integral of x prime dt from time 0 to 2.8 is going to give you x 2.8 minus x 0, right? So then x q, by the way, x q 2.8 equals x q0 plus the integral 0 to 2.8 of v sub q t dt, right? And we were just given that this was -90, right? So we're using fundamental theorem of calculus part 1, trying to find xq 2.8. And this is going to be an exact answer because we're going to use our calculator for it. So using fundamental theorem of calculus part 1 to find another position with a given known position and velocity equation. By the way, you're not going to integrate that equation by hand. So that's why you need to use fundamental theorem of calculus to let your calculator do a definite integral. So we're going to do -90 plus math 9 vars, y vars function y1, I have it entered in there, comma x, comma 0, comma 2.8. We're going to do the same thing for x sub p. Waiting patiently. Take a deep breath. 45 5.93765535. Okay, so we got that work nice and labeled. Now we're going to do the same thing, 0 to 2.8 of x prime p t dt is going to give you x sub p 2.8 minus x sub p 0. Right, this fundamental theorem of calculus says if you integrate derivative, you get the original function, you plug limits in. All right, basic stuff. If you integrate derivatives, they cancel each other out, plug limits in. Now we're trying to find x sub p 2.8, so we're going to move that over there, and we're going to do x sub p 0 plus 0 to 2.8 of v sub pt. So I'm changing the x prime to v sub p because that's what we've been working with earlier. This is just the way I always write it first. And then so we're going to get 2.8 equals 0 plus 0 to 2.8 v sub p dt. Now, we calculated this. They told you, using your answer from part B, this is what we calculated in part B, but it was an estimate. So x sub p 2.8 is approximately 40.75 meters. Okay? So now we can go back here and we can say that the distance between them is approximately 45.937653 minus 40.75 absolute values. And that equals minus 40.75. That equals 5.187 or 5.188 meters. Let's put the units. So, I mean, we could write this a little nicer. I mean, that's all the work. That's the answer. I mean, we could say the approximate, because they did say approximate. This isn't exact because one of our answers is approximate. The approximate distance between the particles is 5.187 meters at time t equals 2.8 hours. This is a nicer version of the answer. So point-wise, it was 3 points. 1 point for involving the integral of EQ. So essentially knowing you're supposed to use fundamental theorem of calculus. 1 point for the position of particle Q, and then 1 point for your final answer. Because we'd already kind of done the work for x sub p before. So, okay. So that's the end of calculated problems. We're going to go on to problem 3, no calculator. And we have a picture of a graph. Now I put the graph down here just to make it all fit on this page better, so we can maybe fit our work on one page. The continuous function, so it's continuous f on a closed interval. The figure above, well below, shows a portion of the graph f consisting of 2 line segments and a quarter of a circle centered at 0.53. So here, this is 5,3, and they're telling you this is for sure the center of this circle. So this is for sure the radius of the circle, which is 3. This is also the radius of the circle, and it's a quarter of a circle. And then these are 2 straight lines. It is known that the 0.3, 3 minus root 5 is on the graph. So where is that at? I guess that's right here. They're telling us that the coordinates of this is 3, 3 minus root 5. So I'm just trying to put this information on the picture to help me. We're probably going to need that at some point. A says to if negative 6 to 5 of f of x dx equals 7, then find the value of negative 6 to negative 2 of f of x dx. Show the work. They'll use your answer, which means show it nice, and use, label it. Okay, so it feels like we should be using some kind of like properties of definite integrals. We have information from -2 to 5, so I think we could integrate -2 to 5 by using geometry in this picture, and then we have -6 to -2. We want -6 all the way to -5. So that makes me think, okay, well, -6 to 5 of f of x dx is going to equal -6 to -2 plus -2 to 5, right? You can break up integrals. So we know one piece, or we know this piece right here, and we want to find this piece, and we can find this one using geometry. So probably writing that down, that's a point right there. Actually writing this down, showing this properties of definite integrals, that's a point. So we're trying to get this. So we're going to say, all right, and well, -6 to -2 of f of x dx, I'm going to rewrite it, is going to be -6 to 5 of f of x dx minus -2 to 5 of fx dx. And so that is 7. And then now we've got to find this integral. So we got to find all this area right here. This area, this area, this area, this area, this area. Okay? So we got some geometry to do. Now I'm going to put these all in parentheses and kind of show my work. So this is a little triangle, 1/2 base times height, minus, since this one's below, this has to be distributed to everything, but this one's going to be negative. I'm going to do this whole run right here. And you can check, this goes up 2/1, so this is definitely at 1/2 right there. So this is going to be, the base is 3/2, 1.5, and the height is 1. Now I already accounted for the negative by putting minus. Plus, there's another triangle here, 1/2. This base is 3/2. The height is 3. And then we got to find this area. Now, the way we find this area is by doing the square minus the quarter circle. So it's positive, but the way we find it is by doing the square, which is 3 squared minus a quarter of a circle, pi r squared. Okay, so that's all my work. This is a little tedious. So let's see if we can keep going right here. Minus, you have 1/2 minus 3/2. So that's going to be, let's see if I did that right. Let's see. Okay, yeah. So we have a bunch of different terms here. We have minus 1/2, or 1/2 minus 3/2. So that's going to be, and then we have a 9/4 here. So I'm going to change everything for us. It's 2/4 minus, this is 3/4. 3/4 plus 9/4 plus, we have a 9 over here. So we can make that a 36/4, just to combine with all these, minus 9 pi over 4, which we cannot combine with those. And so we have -1/4, 8/4, 44/4. Okay, and so then we have 7 minus 11 plus 9 pi over 4. And finally, we get -4 plus 9 pi over 4. That's your answer. That was, okay, so 1 point for the first setup, and then 1 point for finding -2 to 5. So all this work right here, getting this, all this, that was a point, and then your final answer was a point. But that was kind of a lot of work, a lot of detailed work. You got to be careful. But all right, part B says to evaluate the integral of 3 to 5 of 2f prime x. Notice the prime plus 4 dx. So first of all, properties of definite integrals, which seems to be a theme here, says we can break this up, right? We can do this one on its own, bring the 2 out in front. We can integrate this one on its own. You have to integrate the 4. You can't just add 4, okay? And then the antiderivative of f prime is f of x, 3 to 5. And then the antiderivative of 4 is 4x, 3 to 5, okay? And then so we're going to get 2 times f of 5 minus f of 3 plus 20 minus 12. Now, f of 5 and f of 3, we can get those from this graph. F of 5 is 0, and f of 3, oh, that's what they told us, was that 3 minus root 5. Now, make sure you put it in parentheses to distribute the negative 2. Plus 8. And then the 2 gets distributed to everything. So it's going to be minus 6 plus 2 root 5 plus 8. And so the final answer is 2 plus 2 root 5. Now, points for this. Now, the point breakdown of this problem is 3, 2, 3, 1. So the first problem we talked about. So this is 2 points. 1 point for using the fundamental theorem of calculus. So that's where you integrated f prime and you got f. So that's 1 point. And then 1 point for your final answer. Okay. C says the function g, so here's a new function, g equals the integral from negative 2 to x of ft dt. And it says find the absolute max value of g. So we want to find max g on the interval negative 2 to 5, justify your answer. So extreme value theorem, I think, is what we're probably going to use. These are your endpoints. So we got to find the derivative of g, which is going to equal f of x, right? If you take the derivative of the integral, they cancel each other out, but then you got to plug limits in, but then you got to multiply by the derivative of the limit you plugged in. So when you plug negative 2 in, you got to multiply by 0 and it goes away. So g prime of x equals f of x, which means that this graph up here is the graph of the derivative of g. We need to set it equal to 0 or undefined. You need to show all this work. Okay, so this is 1 point right here. G prime equals f equals 0. You should be writing it down anyways, but they generally give credit for that. It's got to be labeled. You got to show it equals 0. You can't just do that in your head. Now, from the graph, when is f of x 0 or undefined? Between negative 2 and 5. Well, right here at negative 1, at 1/2, and then at 5. These corners, it's not undefined. That'd be the slope of f would be undefined there. But g prime, the slope of g, is the graph of f. So x equals negative 1, 1/2, and 5. Okay? And the fact that you identified negative 1 as one of your critical points is worth a point. So these are our critical points. So now I'm going to make a table, like I always do whenever I can with the extreme value theorem. So we're plugging x's into g, which equals the integral of negative 2 to x of f of t dt. And the endpoints are negative 2, and then we've got negative 1, and then we've got 1/2, and then we've got 5. So we've got to plug all those in. Now, the easy one is when you plug negative 2 in, you get 0, right? When you plug negative 1 in, it's the area from under the graph from negative 2 to negative 1. It's that first little triangle, 1/2. It's positive, so that's 1/2. And then when you go to 1/2, it's going to be the area from 0 or from negative 2 all the way to 1/2. Well, that includes this area, so you just start with that, and then you're going to add, and it's actually a negative area, negative 1/2. The base was 3/2. The height was 1. So that's going to be negative 3/4. So we have 2/4 minus 3/4 is negative 1/4. And then 5 is going to be that value plus the area under plus this area right here that we calculated before, which was a square with sides 3 minus quarter of a circle with a radius of 3. So that's going to be 9 minus 1/4. So 35 fourths minus 9 pi over 4. Okay. Now we're trying to find the max. So is it this one? I would estimate this. I'd say, well, this is, oh, did I make a mistake? Let's see. That's 9, 36, 35. I don't know. Negative 1/4 plus 9. I feel like, oh shoot. No, I did make a mistake. So there was another triangle right here that I need to add in here. 1/2, the base is 3/2, and the height was 3. So it's another 9/4. So we have 44 fourths. So that's equal to 11. And it's about 11 minus, now pi is about 3, right? So this would be about 27 point something over 4. That's about 8. So this is about 3, which is for sure the max, right? That's for sure the max. You don't have a graphing calculator to help you on this one. So that's for sure the max. So I'm going to say they wanted the absolute max, by the way, that y value, the absolute maximum of g on the interval -2 to 5 is 11 minus 9 pi over 4. I'm going to give the exact one. Don't give that rough estimate. Okay. At x equals 5 by extreme value theorem by checking endpoints and critical points. Nice, thorough, justified answer. So it was only worth 3 points. You got 2 of the points really early on, and then all the rest of this work and justification was a point. D says, find the limit as x approaches 1 of 10 to the x minus 3 f prime of x over f of x minus arc tan of x. Now, first thing we usually try and do is just plug it in. So we get 10 to the first minus 3 times f prime of 1 over f of 1 minus inverse tangent of 1. Now, f prime of 1 would be the slope of the graph at 1, which is up 2 over 1. So that's 3 times 2. F of 1 is just the value of the graph, which is 1. Inverse tangent saying, what do you take tangent of to get 1? Well, when is sine and cosine, sine over cosine, the same value? That's pi over 4, right? And so, right, because you're asking, what do you take tangent of to get 1? So when is sine over cosine of the same angle equal to 1? Well, that's at pi over 4, quadrant 1, quadrant 3, but we're assuming principal values because it's inverse tangent already given to us, so it's going to be this quadrant 1 pi over 4. So this is going to be 6 over, we could give this a least common denominator, so that'd be 4 minus pi over 4, so this would be 24 over 4 minus pi. Nope, this is 4. 10 minus 6 is 4, so this is 16. This problem's worth 1 point total. So a mistake like that just really sucks. I kind of was thinking, oh, they're going to have us do L'Hopital's rule or something, but they didn't. We didn't get into determinant form. We had to plug it. We had to look up the values and plug them in and evaluate the answer. So that's the last point there. I'm going to do the next video in a separate video just because this one's been kind of long, but this was the first 3 problems.